Hey everyone, welcome back. Today we are going to talk a little bit about the statistics that we may be using in psychology. And so, for those of you who have had perhaps a stats class before, a lot of the information you're going to see in this PowerPoint is probably going to be review for you. In fact, there's going to be some information in here that you learned likely a very long time ago in your math classes. And so, when we go through that, we'll go quickly and we'll talk really about how psychologists can use this information, and then make sure that when you're taking notes that you're writing down what makes sense to you and you know how to apply that into different psychological scenarios. So as we get started talking about statistics in psychology, recognize that there's kind of two main types of statistics that we will read about and discuss. So one type of statistics are what we call descriptive statistics. And with descriptive statistics, you can look at the source information and you can figure out exactly how you came up with that particular statistic. So let me give you an example of what I mean by that. Let's say I give a unit test in my class and I have 25 students in my class. Well, when everyone takes the test, I can come up with an average, right? The class average on this test, let's say, is an 83%. And if someone wanted to know, how did you come up with that 83%? I could show them every single data point. I can describe exactly where the information came from. And so with descriptive statistics, it's a summary of data that you can directly observe. This is where we got it, right? Think about a person's average mile time in track and field. So they run a mile 10 different times and they take the nice average and they can look at the data. We look at a range of scores. So the range of ACT scores for a class at Park Hill, who had the lowest score, who had the highest score, and you can look at the observable data. Now, inferential statistics, on the other hand, you are not looking at the entire population. Instead, with inferential statistics, you are drawing conclusions based off of a representative sample. Sometimes getting all of the observable data just isn't possible. And so, what you do is you take a sample, and from there, you draw a particular conclusion. These are what we call inferential statistics. And so, maybe you have a fast food company that says this cheeseburger weighs a quarter pound. Well, they're not weighing every single cheeseburger that they make. Instead, they are weighing a sample of cheeseburgers and coming up to with the conclusion based off the representative sample that the cheeseburger is going to weigh a quarter of a pound, right? Think about what we talk about in this class with psychology. We'll talk about different prevalence rates for mental disorders. And so we may say something like 1 out of 100 people experience symptoms of schizophrenia. Well, clearly, we're not asking everyone. Instead, we take a sample, and from that sample, we draw conclusions. So those are what we call inferential statistics. Now, looking at the measurements themselves, when you look at this slide, it's going to be a bunch of terms that you're very familiar with, right? Mean, median, and mode. You've been doing that since elementary school. With mean, median, mode, it's essentially trying to have this one number that describes a particular piece of information, right? What's important from this slide that you may not recall from when you first learned this is the title of the slide. Mean, median, and mode are a particular type of statistic that measures what we call central tendency. And that's important. It's important that you know that mean, median, and mode measure central tendency, what tends to be toward the center. Sometimes we're looking at an average, right? That's our mean. Sometimes we're looking at what's just most common. That's our mode. And sometimes we're literally lining up our data and trying to find what is in the middle. That's our median. And so, when you go through the process of finding mean, median, and mode, sometimes you may ask yourself, well, why don't we just always find the average, right? Why is it that we have these different measures of central tendency? Well, it's because they tell us different things. I have on this slide the example of a class that I taught last year, and this interesting kind of layout of grades after the first few weeks of class. So you can see there with this progress report, after the first 4 weeks, the average grade in the class was a 77%. And so if I'm walking down the hallway and a principal pulls me over and they say, "Hey, we're only a month into school and the average grade is a 77%. What's going on?" Well, that doesn't really give a clear picture of what's happening. I could just as easily say, well, more students have a 100% in this class than any other grade. In fact, when I line up all my grades, the middle is still an A. It's just that there's a couple really low scores, right? If you have some students that maybe aren't turning in some assignments and they're missing things, that's going to skew our data to where the average looks really low. So let's take a look at that. In the middle here, we have what is considered a normal distribution of data. And a normal distribution of data is going to be when the mean, median, and mode all fall essentially in the same place. So these different measures of central tendency all tend to line up. A lot of times when we think of what's in the middle, we call that average. But that's not always the case, right? Average does not mean that half of the population is on one side and half of the population is on the other, with average being in the middle. That's your median. But we sometimes, will confuse these terms. What can happen is we have outliers. And when you have outliers, then it's going to bring that average, essentially above or below the median and the mode. And when that happens, we call this skewed data or a skewed distribution. So, for example, if I have a class of 25 people take a test, and let's say most of the students do really well, right? They get maybe a mid B on the test. But then I have one student who's absent that day, and I go into the grade book and I give that one student a 0 until they make up the test. Well, if I look at the test average, it's going to be skewed. It's going to have a left skew, or what we call a negative skew. The average is going to look lower than it really should because there's this outlier dragging it down. And so we name the skew after the tail of this distribution. This is a left skew or a negative skew. Whereas maybe we take something like the average age of the people in my classroom, myself included. Well, if we take the average age of the people in my classroom, which is primarily made up of, you all teenagers, the reality is the average age would probably be around 19 or so because of me, because I am dragging that average to the right. It's a right skew, or what we call a positive skew. So these outliers tend to mess up, I shouldn't say mess up, but they skew the distribution of data. And so you should be familiar with kind of what that would look like. All right. So when you learn in elementary school about mean, median, and mode, you often also learn about range. We kind of tend to lump those together: mean, median, mode, and range. But what's interesting is range is actually a completely different type of statistic. Mean, median, and mode are measures of central tendency. Range, on the other hand, is a measure of what we call variance. And just like with central tendency, you need to know that range is a specific type of variance. How much is the data changing? How much does the data vary? And you are well aware of a range, right? It's simply the difference between the largest point of data and the smallest point of data. And so it looks at this kind of spectrum of data. It's the distribution of the data. But there's another type of variance that you may or may not be familiar with that we call standard deviation. Here's the thing with range. Range tells us, how widely dispersed data is, but it doesn't tell us much about consistency, right? It doesn't really tell us about how consistent that data is showing up. So let's say, again, I give a test in class and the average is an 85, and I say that, well, the range of scores is a 40% to a 98%, meaning there was at least one student who scored a 40%, and there was at least one student who scored a 98%. That's the range. That's fine. That tells us what the best did and what the worst did, but it doesn't tell us how consistently students scored. So our standard deviation, what the standard deviation does is it looks at the average distance that people fall from the average, right? So listen to that again. Standard deviation is what is the average distance students fall from the average. I give a test and I say the class average is an 85%. And I say the standard deviation is, let's say, a 3%. Okay. Well, that means that the average distance for most students was within 3% of the class average of an 85. Another way to think of it is this: I say, all right, everyone, the average on the test was an 85%. And then we could go around the room and say, well, how far were you from an 85%? How much was this person? How much was that person? And so you think, well, this person, they got an 85. They were right there at the average. Your classmate got a 90, so they were within 5% of the class average. Standard deviation, what is the average distance from the average? Now, this isn't a statistics class, and so we're not going to go into the process of calculating a standard deviation. I do have a YouTube video that shows you how to calculate a standard deviation that I will put online. You are free to watch it, but I'm going to tell you that we're not going to spend time going over it because the juice isn't worth the squeeze. It is incredibly unlikely that you would have to calculate a standard deviation for this course. That makes some of you uncomfortable. You think, I want to know how to do it just in case. I'm telling you, it's like a 1 in 20 chance that you would have to calculate this. And you don't get a calculator on the test. And so we'd be talking numbers that are easy enough for you to do in your mind. So if you want to know how to calculate a standard deviation, I have an optional video for that. Otherwise, you don't really need to worry about it. Let's make sure that we understand what the standard deviation means. Look at this chart I have here. If we look at this chart, the mean obviously is right there in the middle. This orange bar, or this kind of orange line here, shows a small standard deviation, meaning that most scores were really close to the average, whereas that purple line shows a large standard deviation. So there's more variance. It's less consistent. Let's take a little deeper look at this here. Okay, there are some numbers that you just need to know. And so you may consider pausing this slide and jotting it in your notes. What I have here is the standard deviation for a normally distributed bell curve. Okay, normally distributed bell curve, the mean, median, and mode all line up. Let me show you where the standard deviations fall. And I recommend you copy this in your notes. So draw that bell curve. What we have here in this center line, that is our average, that is our mean. Next to that, you'll see where it says 34%. What that means is that 34% of the data will fall within one standard deviation above the mean, and 34% will fall within one standard deviation below the mean. Together, these two green areas together means 68% of the information is within one standard deviation. And I'm going to give you an example in our next slide to hopefully help this make some sense. Okay, but 68% will fall within one standard deviation of the mean, and that will always be the case. If we are looking at a normally distributed curve, it is always 68% falls within one standard deviation of the mean. If we go within two standard deviations of the mean, it's 95%. And so that's another number you just need to commit to memory. 68%, 95%, and 99%. Those three numbers, 68% is within one standard deviation of the mean, 95% is within two standard deviations of the mean, and 99% is within three standard deviations of the mean. Let me give you an actual example to hopefully help this make a little bit more sense. So let's take IQ. We know that the average IQ is a 100, right? We talked about IQ earlier. You take your mental age, divide it by your actual biological age, and then multiply it by 100. So if you're 16 years old and your mental age is 16, 16 divided by 16 is 1 times 100 equals 100. So average IQ is 100, and you'll see it down here at the bottom. It's in the very center. Now, one standard deviation is 34% above, and one standard deviation is 34% below, meaning 68% of all individuals have an IQ that falls within one standard deviation of 100. Well, the standard deviation for IQ is 15 points. All right, the standard deviation for IQ is 15 points. What does that mean? It means that 34% of the population has an IQ between 100 and 115. We just add a 15 to the mean. It means 34% of the population has an IQ between an 85 and a 100. That would be one standard deviation below the mean. Or you put them together. If average IQ is 100, we know that 68% of the population has an IQ between 85 and 115. If we go to the next standard deviation over, well, a standard deviation is 15 points, so we just add 15. So now we're looking at people that have an IQ up to 130, or we take 15 from 85 to get us down to 70. So if the average IQ is 100 and we know the standard deviation for IQ is 15 points, that means that 95% of the population has an IQ between 70 and 130. 95% of the population has an IQ between 70 and 130. Standard deviation for IQ is 15 points, so we can add another 15, bring that up to 145. Subtract another 15 from the bottom, bringing that down to 55. So average IQ is 100. Standard deviation for IQ is 15 points. We know that 99% of the population has an IQ somewhere between 55 and 145. That will include 99% of the population. Now, out there somewhere, Einstein's walking around and he's going to have an IQ greater than 145. And somewhere out there, Forrest Gump is walking around and he's going to have an IQ that's really low. But 99% of the population is going to fall between 55 and 145. So let's see if we can figure this out. Imagine I have two classes which received the following scores. My first class had a class average of a 71% and a standard deviation of 3. And my second class had a class average of 76 with a standard deviation of 6. Well, what conclusions can we draw? Well, we know that the smaller the standard deviation, the more consistent the scores. So right away, we can say that my first class, Class A, those scores were more consistent than Class B. In other words, with Class A, those scores tend to cluster closer to the class average than Class B. There's some other things that we can draw here, the conclusions that we can draw. We know, for example, that 68% of Class A has an average between 68% and 74%. If you think about that, right, the standard deviation is 3%. So if we add 3%, that makes it a 74. If we subtract 3%, it makes it 68. So we have 68 and 74. 68% falls within that range. 95% would fall between a 65 and a 77. Again, just adding and subtracting another standard deviation, another 3%. And you could do the same thing with Class B. All right, if we look here, a couple of questions for you. Average IQ is 100, right? And the standard deviation of IQ is 15. So what percentage of students scored within one standard deviation of the mean? I'm pausing so you can think about it, right? Well, 68%. That will always be your answer. What percentage of students score within one standard deviation of the mean? 68%, always, anytime there's a normal distribution. If you scored one standard deviation above the mean, what score did you receive? You scored 115, right? We know that the average is 100. And if the standard deviation is 15, you scored one above, you get 115. What percentage of students score between a 70 and a 130? It's 95%, right? 95% score within two standard deviations of the mean. 70 is two standard deviations below the mean, and 130 is two standard deviations above the mean. All right. Here's one for you. On a normal distribution of IQ scores with a mean being 100 and a standard deviation of 15, a score of 85 places you approximately in what percentile of the population? So you've looked at this, maybe you've paused and you've tried to figure out which one it is. When we're talking about percentiles, we're talking about what percentage of students were below where you are, right? Well, if you scored an 85 on an IQ test and you're thinking where all these other people are scoring, this would put you in about approximately the 16th percentile. A is our correct answer here. And if you're struggling to understand why, let's look at that chart one more time. right? So you scored an 85. Here it is down here. Well, what percentage did you do better than? Well, you did better than approximately 16% of all scores. You're in the 16th percentile. And so you can add up kind of these different groups here, right? 34% would be one standard deviation. It's like 13.6 ish, but we'll just round up another 14% to the second standard deviation, and then 2% on that tail. So we put that together, add up, 14% and 2%. We're looking at about the 16th percentile. All right, last slide for you. This last slide deals with another statistical measurement, what we call statistical significance or a p-value. And the idea behind statistical significance is simply how likely is it that the independent variable is what is impacting a dependent variable, right? Let's say you're conducting research and you manipulate some variable, you have an independent variable, and then you come up with a conclusion. You measure the dependent variable. Well, how do we know that the dependent variable is because of the independent variable, because of what you manipulated? And how do we know if maybe the dependent variable just occurred, right? So I developed my new fancy drink, the brain booster drink. I say it's going to increase test scores. And so my students all consume the brain booster drink and my test scores go up. How confident am I that the test scores went up because of the brain booster and not some other reason? Maybe test scores went up because the unit was more interesting. Maybe test scores went up because it was the best attendance I've had all year. Maybe test scores went up because the questions were easier on this exam. Statistical significance is trying to measure the confidence we have that the dependent variable is the result of the independent variable, right? And so let's look at this kind of the middle of our slide here. What would we say about a research study that finds that caffeine influences attention span with a p-value of 0.03? P-value is the statistical significance. Well, what we would say is we would say that researchers believe that attention span, there's about a 3% chance, 0.03, there's about a 3% chance that attention span changed for some other reason. But they're 97% confident, right? 100 minus 3. They're 97% confident that attention span changed as a result of the caffeine. So we want small p values. If something is statistically significant, it means that we are confident the results are because of the independent variable. Small p values. In fact, if we have a p value that's less than 0.05, we would say it is statistically significant. We're not saying that it's important, right? That's not what statistical significance is all about. We are saying if a study is statistically significant, we say we are confident that it is the independent variable that is giving us the results that we see and not just some other reason. If you're drinking the brain booster and you get a really good score on the test, and I run statistical analysis and my p-value comes back at zero point 0.4, then what I would say is, well, there's a 60% chance that the scores were because of the brain booster drink, but there's a 40% chance that the scores changed for some other reason. So we want those small p values so that we can be confident in our research. I hope that all made sense. If you have any questions at all, make sure that you reach out to me. Come see me or send me an email, and I'll hopefully help clarify things for you. As always, everyone, best of luck.